Hey everyone, so this is the third and final video on natural deduction, and now we're going to get into some really interesting derivations. It'll be a little more complicated. By now you should be proficient at least the inference rules from SD. Today we will be working with SD+, which means there are a couple of more inference rules and some replacement rules which are extremely handy, and they will radically reduce the length of your proofs. So here are the problems that I'll be showcasing. Let's go ahead and take a look at the first one here. This is a simple entailment task. They give you the set up there, and they say show us that this set in fact syntactically entails tilde d. So for these, the setup is quite easy. You're pretty used to this by now, I hope. You put the content of the set as the assumptions, and at the bottom of your scope line you place the sentence to be derived, which in this case is tilde d. So with that set up there, let me just show you kind of the way I see this. Now that every single rule is in play, here's how I kind of see this. I definitely know I want tilde d, that is line 6. And I do see that there is a d there. It is the antecedent of a conditional. So I know that if I can somehow find a rule that allows me to put a tilde on the antecedent of a conditional, I'd be all set. As a matter of fact, there is a rule that allows you to do that. It's called modus tollens. So I want to set myself up to use that rule. I can't as of yet though. So let's see the other ingredients I have to work with. I do notice that I have another conditional, number 2, and it turns out that they share, 1 and 2 share a sentence. E is the consequent of 1 and the antecedent of 2. So the first thing I'm going to do here, I'm going to go ahead and just combine 1 and 2. And the reason for this will be obvious later. Actually, it'll be obvious in the next line. But I know that E is basically useless to me. I saw line 3, and that looks like the consequent of line 2. So I thought to myself, there's probably something I can do with line 3. And so now you'll be able to see how that worked out. So again, line 4, it's simply a hypothetical syllogism. I combined line conditionals from 1 and 2. And then line 5 is simply De Morgan's being applied to line 3. As you can see, we extract the tilde from the Z and the W from line 3. We put it outside the parentheses, and we turn the wedge into an ampersand. De Morgan's is just a radically useful tool. You should definitely have that in your arsenal. Be really good at recognizing the cases or the situations where you can use it. In any case, let me get rid of these here color coordinations. Now we can give or justify line 6. We have all the ingredients for a modus tollens. Look at 4. That's a conditional. Look at 5. That is a negation of the consequent in number 4. That just is the part to the right of the horseshoe in number 4 plus a tilde. That means using modus tollens, I can get the antecedent plus a tilde through modus tollens lines 4 and 5. That's how modus tollens works. And just, try to think to yourself how you would have done this without the rules, the inference rules from SD+ and the replacement rules. It really would have been a nightmare. So you can see how much shorter, I'm sure you can imagine how much shorter these proofs get. Okay, let's do another one. Here is the next problem that I'll be doing. This is how they show it to you in the book. And of course, your task is to take this argument and go ahead and set it up on the main scope line as a derivation. You can already tell this one's going to be a long one. So I've already worked it out, obviously, and here is what I have. It's a long one, but it's definitely worth taking a look at. The premises, of course, go up on top as the assumptions, and I went ahead and placed a conclusion there at the bottom. By the way, it is a biconditional, so I pretty much already know I'm going to use biconditional introduction. So I've already put the triple bar I at the bottom right. I know I'm going to use that, so I've already placed it there. So it's kind of the way I get things going. Okay, since I'm going to use triple bar introduction or biconditional introduction, I know that it requires not one but two subderivations. So I'm going to go ahead and make those now. The first one, the one on top, starting at line 4, goes from the left of the biconditional, the triple bar, to the right of the triple bar, so from Y to Z. And the second subderivation goes from the right of the triple bar to the left, from Z to Y. So there they are. And you can see the first one is a couple of lines longer than the second one. That's why I left the numbers on there. There's a reason for that. I wanted to show you again how much shorter the replacement rules can make your derivations. So in the first one, I'm not going to use any replacement rules. In the second one, I am, and you'll see, of course, they're substantially different. Okay, so let's see. We're looking at 4 through 9 right now. We need to conclude with a Z, and I'm not sure how to get there. By the way, available for me to use is, of course, the assumptions 1 through 3, because they are in the main scope, as well as Y. I'm allowed to use Y, right? So, what can we do here? When all else fails, I usually go for a tilde rule, which is exactly what I did here. So I'm going to go ahead and assume what I want, which is a Z plus a tilde. So there, line 5 is tilde Z, and I'm going to hope to get a contradiction somewhere down the line. Then I can end that subderivation and put a Z on the basically on the first subderivation, the one that begins at line 4. So, well, given this strategy, I now have more to work with. I have the 3 assumptions. I have Y and tilde Z. So let me begin by taking out some obvious things here. I can go ahead and take out tilde X from lines 2 and 5 using conditional elimination. That's pretty straightforward by now. Here's another thing that I can do. Now that I have this subderivation where I'm looking for a contradiction, I can kind of already see what my contradiction is going to be. If you can't see it yet, you will in a second. So I'm going to go ahead and reiterate Y right now. It's from line 4, and I need it to be in the subderivation, so there it is. And I can get out not Y. Make sure you can see Y. Lines 3 and 6, using conditional elimination, allow you to extract tilde Y. Again, line 3 just is a conditional, and because in line 6 I extracted tilde X, now I have the consequent of that conditional. So I have the lock, I have the key. Line 8 is my prize. I can get the consequent of line 3. So there you go. So now that in the subderivation for tilde elimination, I have produced my contradiction. There it is. I can end that subderivation, eliminate that tilde, and there it is. Lines 5 through 8, tilde elimination. That's how I got Z. And for this, again, we used good old-fashioned SD, no replacement rules, none of the new rules of inference from SD+, just traditional stuff, things you've been doing this whole time. Well, now let's look at the derivation, the subderivation beginning in line 10. Let's go ahead and allow ourselves the use of the replacement rules. Well, when I look at this, I actually see one of the assumptions as being extremely useful once it is modified slightly. So here is what I'm going to go ahead and do. I'm going to go ahead and do transposition on 1. that allows me to basically switch the places of the elements of the conditional and eliminate the tildes. So transposition, by the way, it's a fantastic rule. It's let's see, let's go down here. There it is. As you can see, definitely should be in your arsenal. Very handy. Okay, so now that we have that out of the way, let me get this out of the way here. We have line 11 to work with. Now it's pretty clear how we got line 12. That's a simple 10-11 conditional elimination. Boy, did that line 11 come in extremely handy. So now that we have both subderivations for the biconditional introduction completed, we can complete this proof. It is 4 through 9, 10 through 12, biconditional introduction. That's how that one goes. This is longer than it should be, as you can probably tell. Had we used replacement rules in the first subderivation for the biconditional introduction, it would have been, what, 3 lines shorter? So longer than it needed to be, but I wanted to show you the difference between SD and SD+. Okay, moving on. Theorems. Theorems are, well, they're supposed to be derived from the empty set. Essentially, what that means is all you do is draw your scope line, your main scope, put the theorem at the bottom of the main scope, and then try to derive it out of nothing. So what you have to do, of course, is use subderivation rules from the get-go. It's not usually a bad idea to look at tilde rules unless you're working with a conditional. If you have a conditional as a theorem, then I would use conditional introduction. In this case, it's not a conditional. I would go for a tilde rule right away. So that's exactly what I'll set up here. I'm going to take the theorem, put some parentheses around it, and basically add a tilde to its left. And it'll be an assumption for tilde elimination. So that's what I'm working with. Hopefully somehow I can get a contradiction from here, and it seems pretty obvious that I can. If you can't see it yet, let me go ahead and first do a De Morgan's on line 1. So now we have tilde A and tilde tilde A. Let me go ahead and extract tilde tilde A from line 2 using ampersand elimination. And let me go ahead and take out those 2 tildes. We don't need them. So there's double negation on line 3. And now let me extract again from line 2 tilde A through ampersand elimination. And there you have it. There's a contradiction right there. That means we can end this subderivation. We take the assumption, we eliminate the tilde, and now we have our theorem. That's it. Simple as that. 1 through 5, tilde elimination. Alright, one more here. Okay, last but not least, we have an inconsistency. So we need to prove that this set is inconsistent. How do we do that? Very simple. On the main scope, we have to get a contradiction. So essentially what you're looking for is some sentence Q and its negation. Well, what I did for this one is I first looked at the 2 assumptions and I saw their similarities. I knew that if we manipulate one of them, we could force it to look a lot like the other one. So even if it's not entirely obvious at first, I sort of started moving in that direction. First thing I did is line 1, that tilde tilde, I know I can get rid of it. And it's very important to note here that replacement rules can be used basically on embedded sentences. You don't have to get that sentence alone to use a replacement rule on it. If you see a double negation, you can go ahead and eliminate that right then and there without having to get that sentence or that embedded sentence on its own. This is a perfectly legal move. Another perfectly legal move that I can do right now is this. Notice that all I did here is in this conditional from number 3, in the antecedent portion, all I did was I shifted around its disjuncts Notice that first it was green, then blue, and then I just moved it over to blue, then green. That's all I did. That's called commutation, by the way. Fantastic rule. Commutation, by the way, allows you to move around either the conjuncts or the disjuncts in a sentence. Association allows you to move parentheses around, so that's also very valuable to know. Okay, so that's what I did in line 4, commutation from line 3. Now, I notice that the expression in line 2, it could be made, the expression in line 4 could be made to look like line 2 even more. There is a handy rule called distribution. And what I did here is take a look at the color coordination. Maybe it'll help you. What I did is from line 4, there is a section in green, it's G and a wedge, and I applied it to the conjunction in parentheses. Essentially, I applied the G and the wedge to the E, as you can see in the purple region below that. I carried down the ampersand, and then I applied the G and the wedge to the F. So that resulted in G or F. So now I have open bracket, open parentheses, G wedge E, close parentheses, ampersand, open parentheses, G wedge F, close parentheses, close bracket, horseshoe M. This is beginning to look a lot like number 2, not quite yet though. So let me get rid of this. I have to move these, the G and the F around. Notice, to make it look like number 2, we got to just shift those around real quick. That's a simple commutation. So there it is. Now, it's almost there, not quite. We have to use kind of a weird rule. You can see it right here. Let's see. Idempotence. IDEM, idem for short. We have to use that next. So the consequent in line 6 doesn't exactly look like the consequent in line 2. Let's go ahead and change that. All I did was use idem. That's it. Okay, now that that's set, I reiterate line 2, and notice, just take a look right here, that's a contradiction. We have a very long sentence in line 7, and then that same sentence plus brackets and a tilde on the far left. In other words, we have a sentence Q, that's line 7, and line 8 is the negation of Q. That is exactly how you prove an inconsistency. Now, oftentimes we look for the simple ones. We look for A and not A. But sometimes it requires that you use longer sentences than that. And that's okay. With replacement rules, you can actually just kind of manipulate your existing assumptions and force them to look like another sentence, and then you're done. So that's how you do that one. You have a lot of fun problems ahead of you. Have fun.